Hey everybody, I wanted to make a brief review for 3.1 and talk about some of the major high points from that material. And I went ahead and I just selected three significant topics. They are quantum numbers, photoelectron spectroscopy, and electron configuration. Now this 3.1, what we're doing is we're ultimately looking at basically where all of the electrons within an atom are. And we're coming up with like relative visualizations of where they are, because this is all part of taking that shell model that we had, and we're developing, or we're further developing what that shell model of an atom actually looks like. So go ahead and bear with me as we go through this. So the first item of business I wanted to talk about were the quantum numbers. So basically, the way that I like to think about this is I like to think about all of these numbers as more or less coordinates for where specific electrons are. And so every single electron is going to have a set of a total of 4 quantum numbers. They are n, l, m sub l, m sub s. And these numbers are going to come from the periodic table, and they're also going to give you, or they're going to be derived from one another. So n, your principal quantum number, that's going to come from the periodic table. And basically, what row is the atom on? And what we have to think about is this is going to give us all of the possible quantum numbers. So if we look at n for something like hydrogen, n equals 1. Now if we look at n for lithium, lithium is in the second row. So lithium has n equals 1 and n equals 2, because we're talking about all of the electrons within a lithium atom. Okay, now L is a value that's going to have a range from n minus 1 all the way to 0. So it's important to think about what that possibly could be, do some brief calculations on that. If n equals 1, well then your L can only be 0. If n equals 2, then L equals 1 or 0. Now the significance of this is your L value is going to give you insight into the shape of the orbital. So if L equals 0, L equals 1, L equals 2, and L equals 3, you're talking about specific orbitals. So if L equals 0, you're talking about the s orbital. If L equals 1, you're talking about the p orbital. If L equals 2, the d orbital. And if L equals 3, you're talking about the f orbital. So keep in mind those shapes. A spherical orbital is your s orbital. A dumbbell shape is your p orbital. A double dumbbell shape is your d orbital. And then a much more complicated representation of multiple dumbbells is going to be your f orbital. Okay. Now the m sub l value, we're going to derive that from whatever L value we come up with. And what this is going to be is it's going to be a range from negative L to 0 to positive L. So if L equals 0, then m sub L, well, negative 0 is still 0. M sub L is equal to 0 as well. If L equals 1, m sub L equals negative 1, 0, positive 1. Okay. M sub S, your m sub S is going to be either positive 1/2 or negative 1/2. This is your magnetic spin quantum number. Okay, now I'd like to go back to that m sub L value though, and I'd like to think about if L equals 1, what are your possible values? Well, let's think about the shape of L equals 1. That's your dumbbell shape. That's your p orbital. Now, what's important about that p orbital is we always think about it with respect to the axes. We think about it with respect to our x, y, and z axes. Okay, so technically we can reposition this in 3 different ways. We can have our p orbital about our x-axis, our y-axis, or our z-axis. Okay, so we have three different positionings. Now, let's think about our m sub l value. If if L equals 1, our m sub L can be -1, 0, or +1. Okay, so that gives us 3 different values. So I want you to think about that, and then think about, well, if L equals 2. If L equals 2, we've got that double dumbbell shape. Now let's think about, well, how many different ways can we contort that double dumbbell shape in the x, y, and z planes to put electrons there? Well, let's use our m sub L value to answer that question. If L equals 2, our m sub L can range from -2, -1, 0, 1, and 2. There are 5 different positions. Okay, so we can take that double dumbbell orbital and we can contort it in 5 different positions. Each one of those positions will hold 2 electrons, so we have a total of 10 electrons that can be placed within that. So think about the relationships between the shapes, then the x, y, and z axes, and then your m sub L value. Okay, so these are ultimately all of your quantum numbers. Now, as we grow and we start talking about the 2s orbital versus the 1s orbital, that 2s orbital is still a spherically shaped orbital, but it's slightly larger. I'm going to go ahead and draw a quick depiction of that. Here's our 1s, and then I'll draw surrounding that. Our 2s. Our 3s is going to be larger than that. The same thing happens with those p orbitals. The 2p orbital is smaller than the 3p orbital, and so on. I hope this was helpful for thinking about your quantum numbers. So photoelectron spectroscopy is a very important technique. It was the technique that we used and we discussed to show basically how to get away from that shell model of an atom. So in principle, the way that it works is you have enough light energy that you shoot at 1 mole of a specific atom. So you have 1 mole of carbon atoms, and you shoot all this light energy at this mole of carbon atoms, and what you're going to do is, in 1 atom of carbon, you're going to kick off 1 electron. In another atom of carbon, you're going to kick off another electron. In another atom, you're going to kick off another electron, another electron, another electron. So over the course of all of these different collisions, you will kick 1 electron off of each and every one of those 6.02 times 10 to the 23rd atoms. And by doing that, you will kick off every single electron. So each atom is losing 1 electron, but of all the different atoms that you have, each one of them is going to lose basically a different electron. And so essentially what it gives us is a photoelectron spectra. And that spectra, the way that we read it, is we look at our y-axis as our relative number of electrons. Our y-axis, or our x-axis, we look at as our ionization energy. And the way that we look at this is we say, well, this peak right here corresponds to electrons very close to the nucleus. In fact, sorry about that. We look at this peak right here is corresponding to the electrons that are closest to the nucleus. Relative number of electrons. Okay, so then this next peak, this peak that is downstream or further to the right, well, those are electrons that are farther out from the nucleus. But we can look at the height of these 2 peaks right here, and we can say, well, they're comparable in size, and basically they're the exact same height, so they reflect the same number of electrons. Okay. Now, what we can use this for is we can use this to develop our more advanced model for a specific atom. Okay, so now if I look at something like this, I have two peaks that are the exact same height and then a third peak that is significantly higher. And I would go ahead and say that this peak right here that I'm going to put a little star by is 3 times as tall as this peak and this peak right here. Now what's significant about that is, well, this peak right here that I've labeled as 3x corresponds to a certain number of electrons. And this peak right here, or these other two peaks, correspond to different numbers of electrons. So the peaks that I'll label A and B, those are my peaks that are farthest in, and so they represent the first 2 and then the next 2 electrons whenever I'm thinking about a specific atom. But ultimately, these 3 peaks total up to 2, 2, and 6 electrons. Now, what's great about this is that this peak that I've labeled A is kind of independently grouped from this peak that's labeled B. Okay, B, however, is kind of grouped with my peak that I've labeled as 3x. Now, we can use this to come up with an electron configuration. And so we say our 1s electrons are right here. These are and then our 2s are this peak right here. And then our 2p is that peak right there. So 2s, 2p. So the great thing about, I'm going to put the little 2's in here to show our total number of electrons there. But the great thing about all of this is this shows our total number of electrons that we're dealing with. And as a result, we can use a photoelectron spectra to basically look at a specific atom. Or we can look at a photoelectron spectra and guess what atom that we're talking about here. This atom has an electron configuration of 1s2, 2s2, 2p6. Well, that would be none other than neon. Okay, a grand total of, 2p6, not 2p2, a total of 10 electrons that we're talking about there. So this is kind of a good segue into electron configuration, which I'm going to go ahead and look at next. So electron configuration is a good way of displaying where all of the electrons within an atom are, and, well, which electrons does an atom, which shell and subshells does an electron actually have. So if we look at the periodic table, we can look at it and kind of break it down like this. Okay, so this right here, the far left-hand side, I'm going to label as S. That's my S block. The far right-hand side, that's my P block. This middle portion is my D block. And then this section at the bottom, consisting of my lanthanides and actinides, that's going to be my F block. Now, whenever you're writing out the electron configuration for an atom, what you're kind of describing is well, where is it on the periodic table? Where is that atom on the periodic table? Now, if we took something like, let's go with krypton. Krypton is right here, Kr. How do we write the electron configuration for that? We have to account for all 36 electrons that krypton has. The 2 innermost electrons that krypton has are the 1s electrons. So we're going to say that krypton has a 1s2 complete orbital. Next up, we're going to go to the 2s electrons. Well, it's got both of those. So 1s, 2s, 2p, 6, 3s, 2, 3p, 6, then, now this is where it gets a little bit tricky. Well, what we want to do is we also want to include the 3d, which corresponds to these right here. That's a complete orbital. We're going to say 3d10 because we have a d orbital. And whenever you get to the d orbital, based on the photoelectron spectra, that d orbital is a part of this 3 subshell. So it has that principal quantum number of 3. So we write 3d10. Now we go on to 4s2, 4s2, and now we're at the 4p6. Okay, so that's a complete electron configuration for krypton. And it's always good to go ahead and check on yourself and say 2, 4, 10, 12, 18, 28, 30, 36 electrons. So I placed all 36 of my electrons, accounted for my 3d orbital versus my 4s orbital. That 3d orbital comes first because it's a little bit lower energy than that 4s orbital, and it's smaller than that 4s orbital. So that's what I got with respect to electron configuration. I hope this is all helpful for your 3.1 material. Have a good one.